banger. Ooh, I gotta call my friend. Wait a minute, what I say I gotta do again? Minute to minute, I feel like I'm in the movie Memento, but I don't have a pen. Wait a minute.
Okay, welcome to the unofficial CTF write-up of the CSAW Ctf challenge that ended 3 days ago. I know, elephant in the room, I am in a different room. I'm not in the same room as my previous video. We don't talk about it. I'm being given adequate water, adequate food, adequate shelter. I'm perfectly normal, healthy, and sane. Nothing's wrong. Don't ask questions related to my personal life. First off, we'll start with the crypto. Right off the bat, I'm gonna say these two challenges here, Diffusion Pop Quiz and AES Diffusion, I'm not gonna be covering these ones. These aren't really challenges, they're just like quizzes-ish, but they're like more of like a learning thing than like an actual challenge. They give you this little thing here, it's like some ciphertext, and if you just go ahead and go to, you know, crypty, yep, that's the site, that's the plain text. It's a key of, what? -5, so it's a key of 5. And it's just basically like a whole like learning thing about what diffusion is, which diffusion is, it's basically how much the entire ciphertext changes depending on one byte being changed in the plain text. If we do like XOR 1, 2, 3, 4, 5 with the key, and then that's our ciphertext. And then if we just change this one byte to like X, for example, only this byte changes, right? Everything else stays the same. So that's what low diffusion is, and high diffusion would be this. So SHA-256, do that for Halo, and then just text that to X there, and the entire thing changes, right? So as for the actual challenges, unfortunately this one right here, HexHex, it's down. It was hosted by an Amazon bucket, and it got taken down because the CTF ended. So I can't really get the original file I got, but what I can do is I do have a copy of the file. So if I go ahead and go to crypto, then HexHex, Sublime, what is it? So yeah, we'll get this file right here. So if I open it, you'll see it's just like this. It didn't come like this when I downloaded it. I had to like organize it, but like what you'd see is like a bunch of like, you see like a bunch of line breaks. It'll be like very messy and unorganized type thing. Like you'll be like really like jarbled up. So I did organize it. And the actual text it decrypts to, or it decodes to, if you just like put it in a string or something, you can see here, it's just some text. If you just kind of look down here, I did organize them, but you can see here that we didn't have this one registered. Because I don't know, this was very different. I didn't know what this actually was. So it does seem interesting. We're going to copy it down here. If you keep scrolling down here, we'll see another one here. And the rest is really just like hexadecimal characters separated by some separator, like for example, comma, OX, colon, semicolon, all that stuff. So what I did was I went to decode.fr/cipher identifier. And here you can put in any ciphertext to recognize a cipher from. And 99% of the time, if it uses a cipher like that's actually like decodable from decode, it will recognize it. So like if it was a cipher, not like an encryption symmetric algorithm or like a custom encryption algorithm, then like you will know how to decrypt it, like no matter what it is. So if you just plop that there, press analyze, you can see here that it's something called a twin hex cipher with a very high confidence, like basically like 10 to nothing. Just put our little item there, and then we go fake flag, some fake flag. Just do that value instead. Twin hex cipher to code, and there you go. That's our flag. It's just like a needle in the haystack challenge, basically. But you can see here it's called twin hex, and the challenge is called HexHex, like twin hex. You know what I mean? Next one we're gonna do is Trapdoor, and you can see the description says something about 2700 core years. If we go look that up, it's about RSA-250 factorization, which comes in handy. Later on, you'll see why. You see there's a bunch of stuff here, but you really get the message 1 and message 2 in the public keys. So if you just do sublime message.enc1 public key 2, because I don't want to get those done ones. You can see here that the messages we get are some ciphertext value, and then these are encrypted by these public keys. So public key 1 is modulus this one. Public key 2 is modulus this one. So if you go ahead and do pyenv activate an old version of Python, you'll see why. There's going to be a tool called RSACtfTool. It's mainly like a GitHub repository for like common RSA attacks you can invoke on like crypto challenges and CTFs about RSA encryption. So it does like all the common attacks like Windows attack, same NUG attack, small CRT, stuff like that. Just a bunch of complex math that I'll do for you. So just it gets like a quick little, yeah. These obviously aren't PEM format files. They're just like numbers. So what you want to do here first is turn them into PEM format, which is what those public key done files were. RSACtfTool -e, let's do public key 1 first. E this one, and then for the modulus, we'll put the modulus in here. There we go. And we'll do this option here called create pub. And if we run it, it'll give us a public key in PEM format. So now we have our public keys that are done. They're already there before, but like they're gonna be the same thing. There we go. So these are our completed public keys. And what we can do now is we're gonna be doing -- public key. So RSACtfTool -- public key. I want to do public key done 1, public key done 2. And we want the private key from these obviously, and we're gonna go ahead and do just dump key and x. There we go. If we do attack factordb, you'll see here that we have our private exponent for the second public key, and we have our private exponents for our first public key right here. So now we have the private keys for both public key 1 and public key 2. And what I did then was I made a script to just decrypt it by a standard RSA decryption. We just have the two ciphertexts. This is ciphertext 1 in Python, ciphertext 2 in Python. Then we have our keys here. And now for each ciphertext, we're going to decrypt it by just doing the standard ciphertext to the power of private modulus n to get our plain text back. So then we do long to bytes to get it from like an integer to like a byte array. There we go. There's our key. So there we go. Last challenge for the crypto section is this called CBC. We get two files. We get an app.py and an out.txt file. So this is the file we get. It's just a Python file. This is the source code for the server. So if you go ahead and just run this app.py, it says ciphertext, connect to the host here. Same thing. It has some AES key that we don't know, and it has some AES IV which you do not know. It creates an encryption like instance with that, with AES CBC mode right here. It turns it from bytes to hex, right? So like if it's like, for example, bytes to hex, or from hex actually. So 1010, that would just be 10 as a byte string type thing. It just parses it. And then it unpads the data, which I'll explain later. And we basically get if it worked out or if it didn't work out as the output, right? So right off the bat, you probably have no idea what the fuck to do with this, but the vulnerability lies in this function here, unpad. So what this basically is, we also have an out file here, which is just, if we just, it's basically like a bunch of hexadecimal data. And if we like go here to this netcat instance and just cat it out here to this netcat instance, it looks fine. So it is some valid ciphertext. Again, unpad function here is basically PKCS number 7 padding. And we're also going to need to look at the AES decryption. There we go. So we don't need to worry about what this decrypt thing here. That's just the standard AES algorithm, right? That's like the whole block cipher decryption thing. We need to worry about the actual mode that's used here. And keep in mind how these ciphertexts relate to each other. Firstly, we want to understand PKCS number 7 padding. So PKCS number 7 padding, if you just do it Python, we don't really need this anymore. AES works in blocks. Each ciphertext or each plaintext has to be structured in a 16-byte block, 16-byte block, because that's how the cipher works. It shifts the bytes around in like some sort of matrix, and that has to be 16 bytes for it to be filled up properly. So if it's not exactly 16 bytes, then it's just not going to work. So what padding does is it just puts extra data at the end of a plaintext to make it 16 bytes. So for example, if we do data equal, let's say this is our plaintext and we want to split it into blocks. Like this is not 16 bytes. So AES is not going to take that. So what we do instead is we do this here. Pad this data here to 16 bytes. And there we go. So now it's a multiple of 16. And the reason why is it does this. It adds these extra bytes here. And you might be wondering why it's 0xb. Because if we go ahead and add something else to it, it's now /n, which is a new line. And another one, it's /t. It's 7, 6, 5. It's basically because you want to also unpad this data once the plain text gets decrypted. So you want to remove these bytes because they're not really meaningful for the plain text. They're just for AES. So the actual numbers that these bytes use are how much padding bytes you added. So for example, the length of this string here, of only this padding, how much padding we added. If you get the length of this, it will be 11. And if we do hex 11, xb. And if we look here, the new line, how much new lines do we add? Right here, it's 10. So if you do hex 10, it's xa, which is, of course, a new line. That's basically what it does. That's what PKCS number 7 padding does. It looks at the first or the last byte of the plain text and checks that number, because there's always going to be pad, even if it's like a multiple of 16. Like let's do, for example, a times 16, right? Like it's a multiple of 16, right? So if you do padding for this one, it will add this here, which of course hex of 16, because there's 16 bytes being added, is 0x10. And then what unpad will do is it will look at this last byte and check the number, and then it will assume this number means how much padding was added, and it will go back this number of times and remove however many characters there were. The reason why this is useful is because if we look at the AES CBC decryption, you'll see something really funny. There's ciphertext, we decrypt it. Let's say it's some value like, I don't know, AES of C or something. And then we go here, and there's something being done here. It's the ciphertext of the previous block being XORed by this value to get the plain text. And the funny thing about XOR is if we know this plain text, right? Let's say we know the plain text is going to be like A, or for example, like the byte, like ASCII byte A. We can get this value by doing A XOR the previous ciphertext value, and then we'll get this value here. And then if we know that value, we can then go ahead and do this value XOR the original ciphertext value to get this plain text, right? So if we can figure out what this decryption actually is without knowing the key, we can figure out what this plain text is. The question is, how do you know what this plain text even is, right? So this is where the actual vulnerability comes in. Here's the funny thing about padding. So if we do unpad of, let's say, these things here, right? Unpad it, a block size of 16. You can see there's nothing, right? How about if we do, let's say, 09, right? That's where something funny happens, because now it says that the padding is incorrect. Because, again, it will say there's 9 bytes, but then we go back 1, and now suddenly it's 10. So it's obviously going to register that something's wrong, because it has to be 0x9, right? It has to be the same byte for 9 times. So it's going to make an error. And if that error happens, it's going to go to this exception here. And if that exception happens, it's going to say error instead of looks fine. So we know something's wrong. And we can obviously tell what's wrong, because if this errors out, it's not bytes. We already know it's not going to be like hex format. This is probably not going to error out because it's just data. Like, it doesn't matter what it is. As long as it's like 16 bytes, it's like which we know it's going to be. I think it's going to be fine. So that's not the issue. It's this. It's the unpad function. That's 99% of the time going to be what's erroring out if you already handled these two cases. We can then use this to say and figure out what the plain text actually is, because let's say we are brute forcing the previous ciphertext value until we get to some value where this XOR this ends up with, let's say, 0x1, right? If this is 0x1, now it depads because there's only 1 byte of padding. So then after this 1 byte, it just stops. It doesn't matter what's after it. For 0x2, any byte after that will always be wrong, because the only way for this to actually work and unpad successfully is if this is 0x1. And if we figure that byte out, because there's going to be an error for every single time we brute force a byte except for 1 byte, which somehow makes it so this XOR this ends up with 1 as the byte. And now, if we know that 1 is the only possible byte that can be correct, we can then perform 1 XOR ciphertext 1, or the previous ciphertext block, to get this k value. And then what we can do is we can then do this for the byte after it. So let's say we want to figure out the next block, or the next key value. We'll do 0x2. Right? We want to get this format, so where it decrypts or unpads successfully. We have to make sure this also 2. And we can figure that out because we can then just perform k XOR this plain text will give us this ciphertext. We can essentially XOR anything to get some sort of ciphertext that decodes to our plain text in the actual server. And then what we can do, we don't need to worry about this. We can just XOR it and set it to 0x2 from the previous ciphertext. And then we brute force for this one. So if it's 1, it's not going to work. If it's 2, it's not going to work. Or if it's 3, it's not going to work, I mean. For blah, 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 it can never work for anything because it has to be 0x2 by the definition of like what PKCS padding does. So the only way for this to decode successfully is if it's 0x2. Meaning that there's only one possibility where if we brute force a byte and we find one instance where it works out, then they know that byte that we just brute forced, this XOR some value, is going to give us 2. And then we can do the same thing. 2 XOR ciphertext, which we know the byte we brute forced, is going to give us this k value, and we can figure out this k value. And then we know this k value is, we can XOR it by 3. Go ahead and just do these 2 values. We know the k values. We can just set it in the ciphertext. Then we just find this one, brute force it. Is it going to turn to 3? No, it's going to turn to 1. Nope, it's going to turn to 2. And now it turns to 3. Oh, that's right. That's the right byte. It's basically, we keep going back until the correct byte is found, and we just keep going all the way back throughout this block, because there's going to be multiple blocks, right? And once we're done with this block, we figured out all the k values for this block, and then what we can do is ciphertext 1, the previous ciphertext block, XOR the k for all those k's, will give us the plaintext, and therefore we successfully decoded this plaintext from this ciphertext without knowing the key. So hopefully that made sense. If it doesn't, then I guess I'm horrible at explaining things. But the solve script here basically does exactly what I said. So this is our data here, it's out.txt, and this is the IV. The IV doesn't really matter because the issue is the IV is controlled. We don't know what the actual IV is, right? So unfortunately, see this first ciphertext value here? It's XORed not by a previous ciphertext, but by an IV, because that's how CVC works, right? There's no previous ciphertext, and it depends on the previous ciphertext, so it just does an IV to initialize it, We'll just pretend that the first block is just like, we can't get it. Like, wait, let's just ignore it. And then we go ahead and split our data into 16-byte blocks, which is going to be because it has to work. It just said looks fine in the server thing it just displayed to you. And then essentially for every single block, starting with the last block and going down, we do what I just said. We brute force a byte such that we find a byte where that padding oracle attack, or the padding says looks fine. And if that's true, if it does say that it looks fine, it means that the unpadding worked, and therefore we found the suspected byte. And then what we do then is we do this brute forced byte. They mean XOR by our known. This is the known plaintext essentially. The known plaintext to get our key, which is going to be this. And then what we do is we just keep going forward until the entire block is done. And when the entire block is done, we will just XOR these keys by the previous ciphertext to get our plaintext. And if we go ahead, I already ran this, you can see. This is the data we get. This is, I don't know why this is like this, but this is our flag right here, you can tell. It's also reversed, actually. This is one issue with the script, it's reversed. But yeah, it was overall a very fun challenge, though. I did learn how to implement CBC padding oracle. I made a sample script, as you can tell. It's gonna be in the description of this video if you want to use it for like your other things, just to not reinvent the wheel, because I did make this myself. So, but yeah. So that's the crypto section of the CTF.
He sees you when you're sleeping. He knows when you're awake.
OSINT is basically open source intelligence, and there's a bunch of stuff I already did here. Let's go over it one by one. So first we have something called authentic Chinese food. It's not showing the picture. Why is it not showing the picture?
He sees you when you're sleeping.
Alright, that was a fucking disaster. Let's go to automatic Chinese food. It's gonna be the first one we start off at. Yes, we have a Panda Express here. Really cool. I love Panda Express. Look at this image. What do you see? There's a phone number, 718-875. So if you look at 718 as the area code, it's in New York. And if you go ahead and do 718-875 as like part of the phone number, let's just see what comes up. You will be finding a link right here. Brooklyn Gastroenterology. You also have an address. So if you go to the maps of this address, and what we can do here is look for a Panda Express that's nearby this location. Sure enough, there's one right here. And would you look at that? It's the same exact thing in the picture. Remember, the flag format is the health grade of it, the year built, and the owner of the building. So actually finding this building isn't really enough. 434th Street building in New York, and you will look for the information here. And you can see here, we already have one. It's built in 1920. You will find this URL, and you'll see a bunch of information built in 1920 and all that. And you'll see the owner here is B&N Fulton Flushing. Oh, if you just press enter, here's the full name. It's B&N Fulton Flushing owner, and they said to remove the LLC. And one last thing, we gotta look for the food grade. So food reception, health inspections, restaurant inspection results. Let's go ahead and plop in our address here. So what is it? 423 Fulton Street as the address. The restaurant name is Panda Express. Borough, it's in Brooklyn. There we go. We found it. And it says grade pending. And next up we have this little car from India challenge. It's called Rickshaw. Here is the image we are provided. It's just a car with 77 CD and nothing else. Just some license plate, some car. What the fuck to do with this information, right? So firstly, you go ahead and look up vehicle registration plates in India. And you can see here, look at that, 77 CD. There seems to be one that's not 199 CD. And it's related to diplomatic missions. So there we go. You see CD is actually a part of the registration. This is the country who did that mission. So if we go show countries here, we're looking for 77, and that's the United States. So this is a car belonging to some sort of United States embassy in India. We go ahead and just do United States, India embassies. This one, this site here. Go ahead and go to the I for India. Click on that one, and we'll see a bunch of stuff. Again, we're looking for CD right here, CD. So an embassy. And apparently there's only one of them. Only one embassy. We want to find the telephone number of who belongs to this car. So again, the embassy owns this car, and we have a telephone number now. Right here. Phone number is this number. That's Rickshaw for you. Next up we have plane spotting. So this was a cool one. We have some information, right? There was a Russian plane in the United States, and it was parked next to a plane owned by an infamous former president. You all know who he's talking about. Can you find this registration number of this Russian plane, the FAA airport code of where the plane was spotted, blah, blah, blah. And also, can you find another Russian plane that flew to the US? Find the state the Russian plane was closest to. Let's go ahead and just do, so we know it's in June, let's go June. We'll search for what? In-text Russian in-text plane. Let's try that. I don't think from is even a keyword, but here's what we get. We get something related to a, oh, look at that, the registration number of the Russian plane, and that's the airport code. It's IAD for Washington Dulles. That's nice. We already have the Russian plane registration code and we already have the airport code. We just need to find what Trump's registration code was. It mentions here something called Trump Force 1. Let's just look that up real quick. And there we go. We already have a registration number for that. Let's go ahead and just look for a Russian plane. Oh, look at that. June 26th, June 27th. So this did happen earlier. And we'll see here some posts about a RSD 738. You can go ahead and look up the flight history of this flight. So go ahead and go to RSD right here. There we go, we found it. Issue is though, if we go ahead and look at this timestamp here and convert it to, so this is Eastern time. This is actually 5:07 p.m. and this flight ended at 2:07 p.m. 3 hours before this timestamp. So I had to sign up for FlightAware because it literally does not tell you what the history is without an account. It is thankfully free though. I kind of hated that with, I hate OSINT sometimes when it comes to like centralized software, but okay, so now we're back, we're logged in, and now I can see the flight history, and now you can see that there's 2 flights. One of them was from Russia to John F. Kennedy, and the other one was from, get this, 5:07. This timestamp was before the flight ended, and this started at 4:55, 4:55, so subtract. It took 12 minutes to get from 4:55 to 5:07. So let's mark that down. So 12 minutes in flight, we will end up, we don't know where that is because we need to go to the layers and change to a street layer. 12 minutes in general is right about near this area of, and you can probably guess what city that is because it's Trenton. The answer is Trenton. More OSINT is on the way. So, an artist by the name of made a cover of a song I liked, but I don't remember the original composer of that song. Could you help me find the original composer? Let me just inspect. Oh, Z. It's ZWNJ. Song artist. Okay, so we're given this link here. The title value is this same value that we found in the inspect element. And they have a bunch of videos. And one of them, if you go down, it says cover in it. It's Big Brother.
Working hard, daily, some
Lyrics on Streets Electric Shocks. Susumu Hirawasa. I don't know how to pronounce that. That's the guy. That's his full name, last name. So his first name, last name. It's so now and then after you do this, there's another challenge that's gonna open up called Mystery. Remember that composer, same guy we found, Susumu. Well, they made a song when they were part of a band in 1992, and it turns out that the unnamed artist also made a cover of this song collaborating with another artist. What is the name of that artist? So we want to first find his songs in 1992. Oh, what's this? P Model 1992 albums. Interesting. So if we go ahead and look up P Model, let's say cover or something. Go here, and we have links here. One of them is to TuneCore. But they have collab with this guy called
女学生
but maybe just look up P Model, this guy. Oh, look at that. P Model, and this is the artist name. That's OSINT. So let's go over just the 3 ones I solved. So there's one called ZipZipZip. First of all, we're gonna start that off. There is a massive zoomed in fucking response. And what we get here in the zip file is a bunch of stuff. So we get a chunk 0 file with, over here it says some data. And a chunk 1 going there, there's some more data. Open this chunk 2, there's some more data. So what essentially looks like is you have to do some sort of recursion with the zip file to just get the data from the zip file. So let's go back, and we don't even need this anymore, so let's close that off. Let's go back to our virtual machine, and we want to automate this basically to unzip the file, capture the text file, maybe append it to some data or something, and just keep unzipping repeatedly until we get to the end of it. And what I did here is I did a solve.py to essentially, this is just handles like, we have a backup here, it'll copy this to the actual zip file, it's our standard, and that's basically what it is. You should hopefully understand what it's doing, and we'll do python 3 solve.py, and there we go. It will unzip the zip file, and it will run fast. This will take some time.
طول ما انت قادر في طريق حاجة جميلة افرح واستمتع بسحر كل ليلة.
Okay, so I made a shell script because the Python script was too slow. It ran for like 30 minutes and it wasn't even like halfway there. So that was a mistake, sh solve.sh, and there we go. So now it will just handle the unzipping now. It'll be much faster.
في حب في الحياة فين المشكلة اللي مش هتقدر عليها والكل حد دمع ومستنيها وكل اللي راحوا عضمهم فيها والكل واحد حلمي ما يتوقفش.
Iteration 32796, you'll get this massive base 64 here, and if you do ls to get the size of it, it's 161 kilobytes of data that we just recursively recovered from that. Here you go, base 64-d, I already have the autocomplete there. And dump into the file, and then just cat the file. Well, I mean, actually, why did I cat the file? So here we have the file in GIMP, and if we just zoom all the way in, we see a flag here. It's CSAW Ctf easy recursiveness write. Yeah, that's the flag. Okay, so next up we have the Covert challenge. It gives us a pcap file and a keys.log file. So right off the bat, we have a keys.log file. So if we just do like cat keys.log, it gives you these little specific data here, and what we want to do with this data is we want to go to preferences and import it. What's the protocol? TLS, right? I already have it imported, but it's gonna be the pre-master secret log file name, and you'll see why if I hover over it. It'll say so it's RSA session ID, client random. Let's just do client random. There we go, client random. So it's basically that sort of format that's asking for. The pcap will have TLS data and no HTTP data, but once we have those keys, it'll take that data and turn it into HTTP traffic because it'll decrypt it with the keys, right? So if you just look for HTTP now, that's already imported. We'll see a bunch of stuff here. Go follow the TCP stream, or the HTTP stream, I mean. And it will give you this little stuff here. It'll give you a script with a key, destination IP. It'll encode a message in the traffic by sending out packets with the IP protocol's IDs being the letter, XOR, is it XOR or times key, so we have to divide it by the key. So go to conversations, then go to I think TCP, and you'll see a bunch of conversations here. And the reason I found the right port was just because everything else looks random except for this one. This is a very perfect number. All has zeros at the end, so that could be a possible candidate for, you know, something funny going on there. It was 550,000. There we go. And we can just verify this. So that's all TCP, right? Everything's TCP. Go ahead and look, and it's at the IP protocol, and there should be an ID somewhere. Identification. It's not IDs, identification. So look, we have our first number 5445, right? We know that the flag is likely the secret message that they're trying to hide. So we can go ahead, and the flag format for this competition was CSAW Ctf with this, right? So if you get the ord of C, we'll have 99. And if we divide this number 5445 by 40 or 99, so what was it? 0x1545. So 0x1545 divided by order C, we get 55. If we get the order of S, because it's CSAW, right, it's 115, so then we look at the next packet, it's 6325, so 6325 over 115, and again, it's 55, it's a perfect factor. So what you can do here then is go to File and export packet dissections as JSON, you'll see why, and it's already exported, but we'll just export again. The standard should be fine, save that. And what this essentially does is it turns those packets into JSON like data that we can then use in like a script or something to parse that and get all the packet information that way. So we're going to look for ip.id, there we go. And it'll be essentially an array of JSON values for each packet. So and if you want to get the specific properties of each layer, you go to some packet in the array, and then you go to its source, then its layers, and then whatever layer it is, if it's a frame layer, or if it's an Ethernet layer, or if it's IP layer, which is the one we need. The key is 55, right? Because everything turned to 55 when we divided it. And we will load this JSON data, parse it, everything like that. And then for each packet, we'll iterate through each packet, because it's all going to be in order, right? And we will get its source, we'll go to its layers, and we'll go to its IP layer, and then we will get its ip.id, and we'll remove this 0x because that's not relevant, and just get the hexadecimal, and then we'll turn that into an integer via the Python int function. So parse as integer via base 16 hexadecimal, and then we will divide that by the key, and we'll just add on to the flag this thing parsed as a character. Then do python.solve.py, there's the flag. License to transmit covert TCP. It's a pretty simple challenge. Next one, triple illusion. It gives you some images, and we have these 3 images. This metadata gives you flower roses, and it gives you hibiscus. So this is likely a hint, and you'll see why. But what I did to solve this was in PNG files, right? A tool to use this and to easily like see every single like potentially hidden thing. If you do zsteg for all these PNG files, it will parse through everything and get a lot of relevant data. I don't know why it just terminated like that. Here we have, can you crack my secret? Here's a list of numbers, see what they reveal. And it's going to be a bunch of like, 0, 0, 0, 0, 0, 15, 23, blah, blah, blah. And we'll have this, what looks like encrypted data, and we'll have this, or cipher data, I mean. And we'll also have this thing called CSAW Ctf, here's a key. This is not the flag, it's just like a key, right? So it says Visionaire ciphertext, and what Visionaire is it's a cipher, it's like a CSAW cipher that only works on like alphabetical things. And this looks very alphabetical, so this is probably like encoded in Visionaire. We can put this in there, and since this is a key, right? It says here's a key. We're gonna import this whole thing. It was kind of hard to tell what was the key here, but I just kind of did all of it. And we'll put the key here and decrypt it. And there we go. So now this decrypts to this one. Here's a new key, decrypt the secret to reveal the flag. If we look at this thing, right? And also it says meta comment, so that's all about metadata, that's the hint. So Python 3, this right here, the length of this is 56. And now if we just take our data and do d equals, so put that in there, and then put all this in there. There we go, and now we have this convert to a bytes array, so we'll just turn that into like d or something. The length of this is 56, so these are both the same length. And also, if you go ahead and look at what the 0 bytes are, it's 1, 2, 3, 8 zeros. And now let's look at the flag prefix, 1, 2, 6, 7, 8. So the interesting with XOR is that if you do 10 XOR 10 or 11 XOR 11, anything XORed by itself will turn to 0. And because there is 8 zeros here and there's 8 of the flag prefix, this is most likely an XOR. So what we can do here then is do from pwn import XOR, just a simple XOR function that I use. We can go ahead and XOR the D with the like the key here. Oh no, wait, hold on, that's the wrong one. So if we do XOR with the actual key, there we go. So this is the secret XORed our visionary decipher key, and this key decrypts that little secret into the actual flag. That's it with forensics. Let's first go with the 50.1. So diving into Null, there's no binary. It's just a server. So if we go ahead and just go to netcat on the server, we're basically given a bash shell, right? And let's just do our standard ls. Oh, there's no ls command found. Like ID. Oh, there's no ID. It's basically like the server has all the basic /bin binaries removed, right? So we can't do like ls, we can't do like the basic Linux commands to access the file system that are actual binaries, because again, Linux like commands, they're not actually commands, they're just like binaries and /bin. So what can we do here? We can't ls the directory, we can't really do anything meaningful. But what we do have are the commands that are in the actual bash shell itself. So echo isn't actually a binary. This is also a command in bash. So essentially what this means is that we can do something called a wildcard firstly to mimic an ls. So if we do like, for example, like let's just do cat wildcard. So what cat wildcard does that's a good way to kind of bypass the ls not being there. We can do echo and then slash and then that, and that will give us everything that's relevant. And also one more thing, let's make a file called bro or something, right? And do ls/echo/ that. There we go. We're not gonna see our little created bro file. So if we do like grep-i bro, we're not gonna see it, right? Because with Linux, there's something called hidden files. If you do a period before the file name, it'll act like a hidden file, and normally it won't be recognized unless you specifically request for it. That's a little issue that you might run into. So what you can do then is you can then do something called shell option -h in the bash. So that will basically make it so the wildcard recognizes periods, like the hidden files when you do this, the wildcard. So now if we do echo /this/.bro, we'll see hidden files if we set that shell option to on. And there's a lot of other shell options. That's just like the one that's relevant for this case. So if we do echo /home, for example, just to get like a basic thing, we'll see that there's home/bin and home/groot. Set the shell option. And now let's do home groot/this. And we'll get a bunch of things. We'll see home group flag, home group.profile, home group bash rc, bash history. We need to cat it out though. We have no cat thing, right? We can't cat files out. So what you can do instead, this right here is going to pipe the output from home group.flag into the standard input. I'm not sure exactly how this works, but essentially this is a way for you to, because you're redirecting the output. That's basically how you get the flag for this challenge. Next up we have something called mini golfing, and we do have a binary this time. Go ahead and just close that and make a new Geedra project, like open that little decompiler thingy, and then go to our pwn category, go to mini golfing, and go to golf. This is our binary that we downloaded. Yes, select all, apply, analyze. So it's not stripped, meaning that we have the actual names of the files, and we have a win function here that just cats out the flag. So that's where we want to be at, right? If we look at our main function and what executes, we have a bunch of stuff here. We have a for loop here, we have a bunch of stuff going on, and we have a thing that essentially gets our input and prints it out with printf. This is our input. So if we just fgets into this buffer of local 518 and then printf local 518, it's just a printf vulnerability. And then after that, it's an easy hello, do you want to jump to this arbitrary address? And we just specify the address and it will jump it to that address. So that's pretty easy to solve. Only issue is there's pi enabled, right? So we need to find out, because what pi is essentially just a thing with binaries to randomize the location of the function. So for example, if we do object dump -d on this golf binary, these are all the addresses of these functions, and without pi enabled, these would be the same. So if I entered 1 to f3, for example, in this little input here, it will jump to that address, and that address will not change, so that we'll jump to the same address. But with pi, it generates a random value, and it adds that to the function address. So we can't just specify 12f3. We have to specify the pi base address plus that 12f3 offset. It basically makes it so we can't really just use static payloads. We have to have some sort of dynamic leakage of the base address in order to make it actually exploitable. But it's easy though, because with this printf function here, we can bypass that. What a printf vulnerability does is it specifies your input as a format string. So let's just run it here. Let's just do an example of golf. Let's execute the binary. So if we do something like A, right, it'll specify our input back. But if we do %x, it'll act like we're doing this function here. So printf %x, right? And obviously that will just print out hexadecimal of whatever is like the parameter. And if there's no parameter, it'll just be like this something on the stack, right? And we can also specify offsets. So if we want to do like %x, right, it'll be this one and 0. If we just do %x or %2 $0, it will be the second parameter. So it will be the 0 instead of this one. So what essentially we want to do is we want to find something and leak it out to where that will be contain the pointer or the base address of something, and then we can use that to calculate the base address of the main function of the win function. And with the win function, we can then just jump to that win function because we're going to have the base address, so then we can actually jump to it in memory. What I did here is a lot of brute forcing. What I eventually found was this offset right here, 171$P, and this will give us this value right here. The interesting about this, if we go to GDB on golf, I don't have pwn debug actually, pwn debug. Let's just break at main and then we'll just run it. We want to look for the, so you can see here that the main function starts with a bunch of 5s, right? That's the pi base address. Press continue and do %171$P. There you go. It has a bunch of 5s here. This is essentially what I did. So we want to first leak out that value. So if we do golf 171$P, this will be the address of that thing. And then what we do is if we do object dump -d, right, 11223. So if we go ahead and take that, we subtract the address of main to get the actual offset that was generated, and then we can use that offset to generate the address of the win function. It takes our data as %lx, so it just parses our data as hexadecimal. So we just send it off as like a hex string basically, and it will jump to our address. So then go ahead and do the remote server here, go there, and there we go. There's our flag. Again, a really simple example of like using printf to bypass pi. And let's go ahead to the next challenge, which is going to be Nix Philosophies. So Nix Philosophies, go back to our folder for this. This is the challenge. So if we go ahead and open this in Ghidra and press I on this, press yes for analyze. You can see here it's not exactly C, it's C++. And what I did actually was a bit of a cheese this challenge. So you can see here essentially that the main idea is that we have our to std out, it's this here, and our std in will take this input, so we can just like rename this variable to like our input, and then it will take this data, do some mathematics with it, and then eventually this output here will be subtracted by 0x643. And then we'll read from that file descriptor to the buffer, and that buffer will be checked to see if it has this string. If it does have that string, it'll then just read out the flag here. You can see flag.txt, blah, blah. The thing with read is that we want read to have 0 as the file descriptor, because that will mean std in there, therefore we can just send in our input to std in. And what I did here was I basically just like analyzed it dynamically. So do ltrace./chal, I think it was. our input. So let's just put 1, for example. So let's keep in mind our subtraction. So 0x643. We minus that by 1603, and that's 0, right? So let's specify something again. So let's do 1, 1 instead. Now we have 1154, so 1554. That's 49. And if we do char of 49, that's 1. So what about if we do this? 1, 2. That would be 1553. 0x643 minus 1553. You already know what it is. Char of 50 is 2, because it's 1 ASCII after. So how about if we do 1, 2, 2, 2? So now we have 1463. So 643 hexadecimal minus 1453. We get 150. So then if we do 150 minus the order of 2, we get 100 minus the order of 2. We get 50 minus the order of 2. We get 0. Essentially, what this is doing, it's taking our input, converting each character to its ASCII decimal version, adds all those up, minus, I guess, the first character. I don't know why it doesn't count that one, but it then takes all that summation and minuses it by 0x643. We have to get 0x643 as the output. Therefore, 0x643 minus 0x643 is 0. This means it would read basically our standard input, meaning that we can input stuff directly and just type it in. It'll put it into our buffer, and then our buffer will compare it. We'd have to put the string in there. And if that string works, it's there, then we'll give us the flag. So I don't know, I'm not sure how exactly I figured this out manually, but I basically just did 0x643 minus order of r times 4, 5 maybe, 6, 15. Nope, that's too much. 2. Oh, we have 0xEB, so what's 0xEB? That's not valid, so how about 13? How about 0x79? There we go, we have a match. So we have to have 13 r's with 1 y. R times 13 plus y. We get this string here. Dot chow. Put this in there. So again, keep in mind the first character doesn't count for some reason, so we add this 1y in the front there just to make it the proper sum. And we now have a read that's reading from our standard input. So then what we can do here is just specify the string here. So make every program a filter, copy that, put in our string here, make our input known, and there we go. There is our flag. And the final challenge I'm going to cover in the Pwn Challenge Saga is the VIP Blacklist Challenge. We're gonna go ahead and open it in Ghidra. So we have a bunch of functions here. Again, it's not a stripped binary, so that's good. We can at least like see all the functions here. We have this main function here, which just does this stuff with CTFs, and then it has a function called handle client, which is gonna be the actual main for like the purpose of this demonstration. And we have a bunch of things going on. So first of all, we have this rangen function here. This generates some random value by going here. If you just look at it, it sees it by the time, then it just like generates a random character and then just like makes a random character array. So we'll call this like generated, something like that. And if we go here, the generator is actually being used here in the string comparison. So it's first reading out our input from standard input. So if we just do like our input, and it will read 20 hexadecimal bytes, like 0x20 bytes from standard input. And then this is where it parses our commands. So if we enter something called exit, we will just exit the program. If we enter something that's the same to this generated value, it will go check if we have something that's in the whitelist here. And by string comparison of whitelist, it basically means it will check the first item in this whitelist and see if that's the word Q. If it's not that case, I mean that's anything other than 0, I mean that's not the same exact string, it will go ahead to this allow copy function. And in this allow copy function, it'll essentially just read our data from standard input into this buffer, so let's call it just buffer for now, and then we'll just iterate through the length of the string Q, and it will check basically if for every letter in this string, our input is the same as that. Well, the thing is, if you check the length of Q, you probably already know this, but like the length of Q is 5, and we read 32 bytes, And 32 bytes is a lot more than 5 bytes, don't you think? And also, keep in mind that it doesn't check if the entire string is Q. It only checks if the beginning of the string is Q, basically. It iterates throughout every character in this string, and once that's done and everything's fine, it will just stop looping. It will not check anything after that. It will copy from this whitelist of I minus 1 times 6 again, because there's like 6 characters in each portion of the whitelist array. It's like a string array, or an array of character arrays. This looks a bit complicated, but essentially what this does, it will push everything down. So if we do I of 3, it will take I minus 1, which is 2. So if we go ahead and do 0, 1, 2, it will take that, and it will shift it to 3. So 0, 1, 2, 3. So ls will go down here. Exit is at, now we're going to decrement by 2. So we can go ahead and do 2 minus 1 is 1. So 0, 1. And then this is 2, so 0, 1, 2. Exit goes down here, and then clear will go down here. You get the point. It will set this whitelist of I, or this iterator, to our buffer. So essentially what this does so far is it pushes our whitelist down, and it will copy our buffer, whatever we input, into this whitelist here. Keep in mind, we can input more than 5 characters, so we can go after our allocated part in the array, if you know what I mean. Just keep that in mind. We can potentially overwrite this array with like some sort of overflow attack. But the issue is there's something called safety being run, and it will run safety on whatever this is, this local 6.8. If we go and look at the local 6.8 values, you'll see exit backwards because little endian. You'll see clear with a null byte at the end. You'll see there's a null byte there. You'll see SL, which is LS backwards. Basically, these are what I'm guessing to be the allowed strings that can be in the whitelist. And it will then go in the safety function here. It'll check if the Q thing is in the whitelist. If this string comparison returns false, meaning that the word Q is not the first thing in the whitelist, then this U will be 0 because booleans are either 0, false, or 1, true. It'll start at 0. But if Q is in the whitelist, that will be 1 because boolean true is also 1. So that will be 1, meaning that we start at 1 instead of 0, meaning that we skip the Q because again, Q is at the top, everything else at the bottom. And then we essentially just iterate through the entire whitelist. So if we have 6 or more characters in our command, it will not allow us, and kick out is a bad function, it'll just exit the program. So we have to ensure that every single string in the whitelist is less than 6. And we also have to check that this here, this string length of the let's call it allowed commands. If this command string length, we'll take that string length and we'll loop through that entire string basically. If we look at like clear, for example, so clear will be let's say for example clear is here. We look at the first character. Is it C? Yes, it is. Okay, continue. Is it L? Yes, it is. Continue. E? Yes, continue. A? Yes, continue. Keep in mind the fact that it checks the prefix of our input only, not the actual entire thing if it's longer than the actual allowed command. For example, if we do LSL, that will register past the safety function, and this safety function will allow it. Because it's LSL, it has LS at the beginning, but then after LS is checked, it won't check anything else, it'll just stop. It won't check the rest of the string. And then after all that's done, if our input, if that exists in the whitelist, then this bvar1 will be true, so we'll call it allowed command basically, because it's in the whitelist, therefore the command's allowed. And if the command is allowed, we'll check the command. So if the command is Q, then we'll just check our position in line, which is going to be this, local AC. But then we also have this thing called here, it's called popen. And popen is interesting, because if you do popen here, it will execute a command via a shell, and it will just run that command. So what that means is that, so we have commands clear, exit, and ls. Okay, let's do ls. You can see here that ls is actually being run. There's no logic for implementing ls here. That's because it's being called here, popen lsr. It's running the ls command. And the interesting thing is, popen runs as like a shell, so bash-c and then our command. So this can be very important because we essentially have, if we use this right, we have arbitrary command execution of the host. So let's go over what we know. We know, number one, if we somehow know that the random generated function, it generates with the time, right? The current time. And this can be predictable. If we can figure out the time, which is going to be pretty easy, we can then seed ourselves like a random generator, then generate this value. And once we generate that value, we'll be able to get into that VIP section like here, right? Number two, if we go to allow copy here, this read function will take 0x20 bytes and will only check the first 5 bytes if the word is Q. And number 3, I guess, are we on? It will push everything down and then write on the top of our array our data. So we can overwrite the array because we have more than 5 bytes that we can, write to. This safety function here exists, but also it only checks if the prefix of each command is the same to the allowed command. So keep in mind that ls runs as a subshell, right? So if we do something called ls-sh, like this, semicolon-sh, we have a shell that also runs after ls runs. This means that we run this and we'll have ls run, but also a shell will run and we'll have command execution into the host. First of all, we use the libc RAM generator function by loading cdll and just loading libc into Python, and then we'll just seed the RAM generator by the time, and then we'll generate that value by essentially generating 10 values, because again, if you look at the function here, it will have it done 10 times, because 0 to 10, less than 10, so it's 10 times. 10 of these values of this random value modulus 0x100. It'll generate numbers from 0 to 0xFF, basically. And once that's done, it'll generate this as a byte string, and it'll essentially send this off to our VIP blacklist binary. And after that, keep also in mind, I forgot one more thing to mention, read has a particular thing where you can also read null bytes. So using that also, we can generate this here. So we can generate Q, right, to have this met, right? It starts with Q, right? So it doesn't check anything else after that. So we just have Q there. And then we have our commands here. So we clear is fine. We just leave clear alone. We can just leave exit alone. But ls is a small command, so we can also tack on 3 more. So this will be 1, 2, 3, 4, 5. 5 letters. Exit has to be, we have to add an extra null byte just to make it aligned properly in the array. So, and essentially what this does, if you do p.interactive, so sometimes it might have a bit of like thing, because the time might not be synced up, just like make sure the time's like proper, but like it will work when the time's like synced up and everything. So you can see here that it will generate this random value and send that off, and then this will be allowed. I don't know why it says command allow, but it will be allowed because it says ls semicolon sh here. And then you can see here that everything worked fine, and we have q, clear, exit, and ls dat or semicolon sh. So if we go ahead and just run to the server, and there we go, look at that, flag.txt. We can just go ahead and cat that out, and there we go. That's our flag. Now off the final challenge.
I know it's hard to remember the people we used to be. It's even harder to remember.
Alright, so welcome to the web section of the CTF. I know I kept you here for so many years, but don't worry, my sweet child, it's almost over. And I did everything apart from the Bucket Wars one because I don't like the cloud. I don't like Jeff Bezos being in my house watching my every move. So playing on the Backcourts, first of all, I'm not gonna be covering this one right now because it's literally like dead. It's gone. It's down. And so if you go to get eval, right, it will do deep eval on it, which basically just evaluates whatever the fuck we send it. The solve script was literally like so easy. Solve.py. We evaluate this thing right here. It casts the leaderboard here. That's basically what it was. So, and you can trust me because I had the flag submitted when the CTF was going on. So, next one, we have logmein.ctf.csaw, and this gives us the source code. Bunch of shit here. So let's go ahead and just cat all the py files out first. So here's the actual logic here. There's the flag. Well, let's go ahead and just Control F to find what the flag actually is. So the flag will be returned to us if we go to this user route, and we go ahead and send something to where our user info ID is equal to 0. Essentially, we get a cookie that's called info from this request, and we decode that with the util function here, so decode. And decode, basically, there's an encryption key in the environment. We essentially just XOR our cookie token with the encryption key. It's basically an XOR chosen plaintext attack, like I'm gonna be honest with you. When we make a cookie, right, it's gonna be in this format. It'll dump this as JSON, so it will turn this as a string, and then just encode it, basically. So it will set our user ID to 1. It's always gonna be 1. Username, let's just call it Brad. JSON.dump s. Here we go back there, and that's our ciphertext. If we go ahead and print v out, right? So we know that the user ID is here, so we're gonna go ahead and do v.index of 1. That's in 48, and then we go ahead and do ct of 48 is equal to order of 1 XOR the ct 48. So now this will just be the key value. And then we just do ct48 is equal to 0 XOR that key. It's basically just like a bit flip attack, but it's XOR, so it's like not even like clever. And there we go, look at that. The user ID is 0 now instead of 1. Use that as the cookie, and then that will be user ID is equal to 0, and we get the flag. Next up is Lost Pyramid. This was a fun challenge. We get something called King's Lair if our role is equal to royalty, and our current date is equal to King's Day. So, and decoded, by the way, is our pyramid cookie. We decode that via JSON Web Token. You know how JSON Web Token works, right? Like basically, like it's if the hash is wrong, then like it's not a valid token. If it's right, then it's a valid token. That's basically how it works. That's number 1. That has the flag. That's what we want to happen. We want to have our current date be set to King's Day, and for this JSON Web Token to decode properly. Number 2, if we go to this endpoint scarab room, if we go here, King's safe list has just a bunch of, these are irrelevant, these are just Unicode stuff, but it also has these semicolons. If we're posting to it, we're gonna have a form parameter called name. It will check if we have a name, and if we have a name, it'll filter out only the numeric and alphabetical values, except for these curly braces. And also, there's a render template string thing here. If we go down here, there is a server-side template injection vulnerability here. These braces are allowed, and also to run template code, you use these 2 curly braces. So if we have some sort of parameter, curly brace, something, curly brace, it will inject here, and that will run via the Jinja rendering engine. So we have some limited injection sort of code execution, but not really vulnerability going on. But keep in mind that the globals are also being set here. That basically means that we can read all the data from this app.py. You can notice here that underscores aren't allowed, so we can't read the current date, we can't read the private key, but we can read the public key and the King's Day. So we can read this value via doing King's Day, which will basically just tell Jinja, get this variable and return the output in this template. And we can also print out the public key. So we can print out both the King's Day and the public key variables. We can't print out the private key. So since it's a JSON Web Token that's with a RSA key, we can't print out the private key unless we somehow factor the public key, which is not the solution. But keep in mind that it takes any algorithm that's the default. It doesn't take a specific algorithm, just any default algorithm. So if we go up here, look at all the algorithms that we have at our disposal. One of them is HS256, which is HMax SHA 256. If we go ahead and do JSON Web Token dot encode hi with that's our payload, just a test payload. And now if we go ahead and do decode, that decodes fine, right? But also we have let's say we sign a JSON Web Token that's malicious, so hi bad actually. Set this to HS256 and set our key to the public key. Oh, there's also some extra garbage we have to do here. Hold on. Now we have our encoded key, and let's go ahead and decode it. Where is that? There we go, decode. It's a valid JSON Web Token. There was no verification error. There was nothing wrong with it. It was decoded just normally. You might be wondering why the fuck that happened. The reason why is because instead of using the public key as verification, like you know how RSA signing goes or asymmetric signing goes, we use the public key which we can obtain properly from that server-side template injection. We can use that as an HMAC 256 SHA key when this token is decoded via this function here. It acts like this is a secret key when it's not. It's a public known information thing, and it will decode it, and this data will be marked as valid, and therefore if you go down here, this code will run. Assuming that's all correct, it will send us the King's layer, and we'll be able to see the flag. So let's go ahead and see this in action. There we go. We send in our data here at the Scarab room. We specify our payload, and our payload, I believe, is a name, and it's the variable. So this is a function that basically just fetches the data of a variable. So we fetch the public key out, and we fetch another variable called King's Day, and we use those to sign a payload with the King's Day and the role. We encode it with that key that we just fetched with the HS256 algorithm, and we get the King's layer, because that endpoint is the King's layer, and then we do cookies of pyramid token, and then we just get the text of that endpoint. God, I need fucking water from this. Okay, so the last challenge is going to be Charlie's Angels. It gives us a zip file, and it gives an endpoint here. Basically, the source code, we'll look at the source code first. Let's go ahead and look at the two things we have here. So we have a node and a py folder. So let's go to node first and sublime all this JavaScript. And go ahead and go to the py folder and sublime all this, just this app.py actually. So number one, the flag is in this py folder. And number two, looking at this Docker compose, we have basically what looks like an internal network and an external network. So this node service is on external, meaning that we can access it outside, and the Python service is internally, meaning that we can't access it from like the outside. And if we look at the index.json or fucking JavaScript place, you can see here that there's a post request to the backup site, and the backup is this endpoint here. So it's basically just requesting to this Python web service internally whatever data is being fed here. Basically, it will take, ignore this, it's not really part of the source code, but it will check if our request has files in it. If it does have files in it, it will check if the file name is banned. It will ignore it and just return error. Otherwise, if it's any arbitrary file name whatsoever, it will basically just take the data that we sent out and just upload that file to the backup / whatever it is. And also we have here a restore endpoint. It will join the request.args.id, so the get variable of ID, and it will check if the file name, if the file does exist, right, that we're requesting. So if backup / id.py does exist, then it will essentially execute that script. Assuming that the output does not have the flag prefix in it, it will send this data out as a web request back to the sender. So you can probably already see here, the goal is to upload a file that's a Python script, have that execute, and basically have it read out the flag, and then have our flag presented to us. Only issue is there's no file upload anywhere in this JavaScript. Again, it's all as post parameters. It has some extra data, so it's multi-part, which is important. Like for all these parameters, except for the talents parameter, it will only accept it if it's a string, nothing else, except for the talents, because this can be anything. Now that we know all this and know what's happening, let's go ahead and just, first of all, on Docker compose up. So it'll have that all working out. Just wait for it to finish. Oh, there we go. It's taking up so much goddamn resources, Jesus Christ. Bro, it's still going? Are you kidding me? What? I hope you know that I started this video at like 11 or so in the morning, and now it's 2:25 and I leave at 2:50. I leave in 25 minutes. It took 4 hours to film this whole video, so I sincerely hope you watched all of it and you give me your life savings, because this is atrocious. You're actually trolling me right now. 99,000 bells in interest? What the fuck was I doing? It's been 1,000 seconds. It's been 1,000 seconds. They all open in 4 minutes. Every single store is closed until 4 minutes. 2:34, I have 20 minutes left. What? No. I think Callie just crashed. Okay, cancel. Oh, that's because the internet's down. God, that'll be so baller. If network. We don't. I don't even know if we do or not. It's hard to tell. We have some connectivity, I think. Okay. Are we rolling now? Okay, now I guess now we don't. Oh, we do now. Oh, the ping is just fucking high. Okay, like 1,000 millisecond ping. Now we're at 23 again. I have to leave soon though. That's the big issue. I have to leave soon. I'm just gonna cut the video until I get back. So, yeah. Okay, so it's been God knows how long, and I am finally back. So you can probably tell just by the lighting change, it's been like fucking centuries since for this to download. So, I don't know where I left off at. So I'm just gonna assume that you know everything. Let's just do a normal curl request. So curl -x post on, I believe it's, I have to also port forward it, right? I think it should be 1338, right? I don't know. I just stopped the container. So this is fucking horrible. Come on, forward stop. Let's do a normal request here. Test.py we'll call it. So from requests import posts. And I also set up on the Python server it's just something that would print out the request data, because remember, HTTP requests are just text, they're nothing else. They're just string and headers and all that stuff. The data we'll print out here is basically the raw request, which will be a string, obviously, because it's just text. So it's basically gonna be a JSON structure with a bunch of values in it. So let's go ahead and set them. And now, this is where things get interesting. So first of all, let's start with the talents being a string. So talents, let's just call it A for now, right? And we're gonna print out the text, doesn't really matter. So let's just do a post request on the test.py here. And there we go. So this is our request that comes in. And I also printed out what files we recognize. Keep this in mind also. There's one thing we haven't taken advantage of, which is the fact that talents can be anything. That's not checked here. So it can be like, for example, an array here. So let's do, you can see here, talents 0, talents 1, because this is how JSON data is actually received, I'm guessing, from this Python server. It's just like a sort of formatting to express objects in, again, strings. We can also control this arbitrarily, because if we do something called like JSON key of X, and then just do Y as the data, post this here. Look at this, Angel talents X. What if we also do something like this here? So X and then just like a Q or something like that. Look here, X and then Q. We basically have an injection here basically, because if you look at what files are, we can see here that the only thing that differentiates a file name from post data is this extra file name header here for that data. Let's go ahead and just, first of all, let's do something called like X, right? Just X. And then let's do a file name equals, I just also want to do this here, the single quotes, just to avoid that little confusion with the double quotes, hello, or something like that, right? And what we can also do here is we can specify new lines also. So let's do a new line. And then let's do k equals a or something like that, and then that'll be that. We want to go ahead and do this and then that to denote a new header. And look at that. We now have one file registered by the Python server. File name hello, k equals some, that's just some line, then that's our data, angels, talents, x, and then file name. And now what we can do here is take advantage of this and do file name hello, maybe like .py or something. And now if we go ahead and just take a look at this Docker file, so exec-it, there is our files here, hello.py. Now of course we need to do one more thing, because this is how we actually make our script run. It will do this restore thing, and this restore thing will take an ID, which will be request.session ID. So basically the file name has to be specific to our actual session ID, our solve.py script. And this is the actual request here. So first it will curl this URL. Let's do that URL will be fine. We curl this endpoint here just to get some random angel assigned to us. And we take that session ID, store it here, and then after that, we load that session ID and then put a .py at the end. And then we run our exploit here, so a and then comma file name as an injection. And then we post this to that endpoint, and the exploit.py script is the actual data of the script. This essentially just reads out the flag, because again, it's located at right here, flag. It will then load the session ID, so then we'll execute Python 3 and then our script here, and then we'll just basically read the flag out and give it to us. You kind of already know that you're very smart. You understand what I was saying before I even said it, probably. This is our injection, so angel, talent, and then some random value, and then file name here. And hopefully you enjoyed me waiting almost 3 hours for this Docker file to install because of the shitty internet that we've been blessed with at this university. So, bye.